problem of distributed consensus into like 3 different classes. And if I'm not mistaken, 2 of them, I believe, introduce some sort of partial synchrony to solve the problem. But I think there is one other option, which is the one we're choosing, which doesn't require synchrony. And I'm saying a lot more than I understand about this paper, but my point being that we've now got a method of coming up with a consensus that doesn't violate FLP, right? And Greg says he can come up with a toy model of it. So this is what we've been needing as far as Casper goes. Mm-hmm. But like Jim says, you know, there is no proof of stake. But to me, this still seems like a big step.
Oh, yeah, definitely.
Which algorithm are you talking about?
Gary and Jim talks about this paper that Greg mentioned, mm-hmm. or error correcting codes.
Yeah, I'll put the link in the chat. So now I'm wondering how far we are from understanding what we need to know about this paper to actually implement something in code.
Well, how new is the paper?
Ask that again.
How new? When did the paper come out?
Oh, it's quite old. It's 2002, I believe. There was one. This is the only date I found on it here, the 2002. And I'm surprised that it hasn't come up before now. But down here at the bottom was where see, this is what I'm getting at. See, they say here that this observation of this input vector leads to another way to characterize the set of conditions that will allow to solve the consensus problem. So the vector that we provide is our guarantee that we will achieve consensus.
Wait, so is that to say, like, depending on what that input vector is, we can immediately say whether or not we can come to consensus?
Well, yeah, I'm something along those lines.
Yeah.
Why? What do you see a problem with that?
No, not specifically. I guess that's just a little bit surprising that, well, maybe it's not so surprising. Maybe I just don't fully understand what's going on in this paper yet.
Yeah, because I mean, there's a lot of ways that they could, reach consistency with a vector. I mean, if anything, this could be like a vector clock, and this could be what do they call it? CRDT, conflict-free replicated data type, where each node or each validator eventually has to like put their mark on the bit string, and that's how you know who's seen it and who's last updated it, and whether it's a fork or not. I don't know if that's what this is.
Yeah, that idea occurred to me, that the problem of, are we really just, is this getting back to electing a leader?
Mm.
And this for replicated data type, this is like majority of votes in a sense.
So it's requiring a consensus before we get around to deciding consensus, huh?
Well, actually, I don't know if CRDTs qualify as consensus. I think they're just their property is just that they're eventually consistent, and that they can guarantee consistency.
Exactly. Yeah.
So maybe this has some other part.
Isaac, do you know more about this paper? Can you tell us something?
I know basically nothing about this paper. I saw there was a link in the Discord, but I didn't get a chance to read it.
Yeah, okay.
And I know next to nothing about error correcting codes as well. So just to put the icing on the cake there.
Well, I know a little bit about error correcting codes, and what they're getting at here is the idea of being able to fortify our data stream in such a way that we can actually get erasures, the number of erasures we get and can correct for is dependent on the amount of waste we inject, or not waste, but information we inject back into the stream.
Are you saying that we put some additional data that are not needed just for the purpose of computation, but do we put some kind of additional data just for like code or just to connect it?
The simplest example would be a checksum.
Yeah, I'm thinking about checksum. Yeah.
Right, that's
Okay.
error detection, not correction. So, checksum.
Yeah, it's only detection.
Yeah.
But you can have something that can correct.
Have some redundancy. You can determine where the error is. And I don't remember much from school 40 years ago. But I mean, it's an information theoretical approach. You're trying to supply a minimum of extra information in order to be able to correct errors, you know, of 1 bit or 2 bits or 3 bits. You need more redundancy to correct more bits of error.
This is interesting. This guy from Hashgraph was mentioning also something like that. That in each message you'll put some additional byte or something that has some meaning, but he didn't explain what exactly.
No, the way I think of it is, you know, the simple case of a fault-tolerant system with, you know, where you have 3 computers doing the same thing, and if 2 of them agree, you go with that, and the other one's considered a fault. And so, you know, this is in essence what it does is you get, you know, if you see 2 1s and a 0, you well, you output 1, but there's, you know, the information loss or the entropy of the error, so that you're getting rid of the noise.
Yep. In electronics, the noise can be if you have very long zeros and very long ones. So you want like a good distribution between 0 and 1s.
So this, by reducing this to a code theory problem, we're in an area of something that we know a lot about.
So in this paper, is the idea kind of like take a consensus problem and try to make some correspondence with like a problem encoding theory where, you know, like Byzantine faults map onto some known notion in coding theory, and you know, maybe something else in consensus maps onto something else in coding theory? Is that kind of the approach they're going for here?
I think so. They do want to say that there is a correspondence between error correcting code and distributed consensus.
Yeah.
Now,
They say in the introduction, Byzantine and value domain faults correspond to corruption errors, which I guess is pretty intuitive.
yeah, it seems pretty natural that, you know, an unreliable reporter is no different than a flaky memory location.
Yeah, that's what they say in the summary. They say, in particular, crash failures and distributed agreement problems correspond to erasure failures and error correcting codes. In Byzantine and value domain faults correspond to corruption errors. I just can't imagine how you can do this without a proof of stake. What protects against a stable attack.
Yeah.
Someone else want to share the screen? I'm kind of flailing about again.
There's the algorithm that they give that you ended on there. I guess the one thing that I have some concern about is the model they use is based on a shared memory with a single writer and multiple readers.
But I thought they said that it could be either shared memory or channel, communications over channels.
Yeah, message passing.
Message passing, yeah. I've got someone at the door. I have to step away.
Did anyone read up on Casanova?
Unfortunately, no.
Yeah, same. Still haven't made time for that.
Oh, hi, Josh.
Hey, guys.
Hey.
What's up, Joshy?
Just got in a minute ago. So you guys are looking at the error correcting codes paper, it sounds like?
Yeah.
Did you read the paper?
No, I skimmed it. I want to. I was curious. One of my prerequisites was going to be, before reading that particular paper, trying to figure out what error correcting codes were. Did you guys already talk about like the basics or how those work? I don't know that.
That'd probably be a good start.
Yeah. Yeah. I also don't know the answer. I don't know how they work either.
Yeah, I know that error correcting codes were like one of the last things I could have covered in the cryptography class, but like I didn't know anything about it, so I didn't. But I learned a magic trick that involved error correcting codes, and you basically can like put down a bunch of quarters. They can be like heads or tails, it doesn't matter, and then you can essentially have like have a letter corresponding to each coin essentially, and like flip one and somehow figure out like what letter they wanted to choose from the beginning, like not knowing the initial configuration of the coins. But I'm not sure I could fully explain all of the things that went into that, because it was kind of more just an algorithm and less an understanding.
Yeah, I think you showed me that trick at one point. I don't remember exactly how it works though.
Yeah.
I didn't realize it was an error correcting code trick.
Yeah. So what it came down to was you always had to have a power of 2 quarters. So like 4 or, 8 or 16 or whatever. I think 16 was the most I could ever do it with. And essentially what it came down to was you were looking at like, so it was like a power set, so if you were doing 8, so it'd be like, a power set of 3 elements essentially. And then depending on like some set inclusion, you could figure out what letter they had chosen. But like I said, that's about all I can remember from it.
Yeah. What letter? So the sort of like victim or trick receiver thinks of like, you give them a set of letters, or you say like, think of one of the first 16 letters or something?
So yeah, I think if you have 8 coins, then I guess you get a choice of, any of 8 letters. I'm like forgetting a small piece of the setup that's like totally crucial. So yeah, I don't know.
Yeah.
I know it had to do with something called Hamming codes, which are error correcting codes, but
Oh, I've definitely heard that phrase before.
I do know what the Hamming distance is. That I certainly know, but I don't know anything about error correcting codes.
I just seen it on the Wikipedia.
Yeah.
Yeah.
Do you want to tour
I
us?
mean, you know, just to think about it simply is you go back to a checksum detects an error.
Yeah, right.
Okay, now if you add additional information, you can narrow down where that error is.
Mm-hmm.
You supply additional bits of information. And
You know, the theory behind this is what they based on these hot drive swaps, where they could take 8 hard drives in a bank and just pull one of them out without any loss of information.
Yeah, because they like have redundancies.
Yeah.
Yeah.
And it's, you know, that kind of stuff is obviously thought through. I mean, it works.
Mm-hmm.
Otherwise, you couldn't hot swap these hard drives in and out.
Yeah.
But that would be good for us, because if we could map this onto a problem that's already working,
Mm-hmm.
it would save us a lot of time when it comes to these deadlocks and concurrency bugs that start introducing themselves.
Yeah, it'd also be a really efficient way to represent consensus in a program.
Mm-hmm.
But I see rolling as a solution for this problem. Like, we want to write this kind of stuff in rolling, right? And not the other way around. But for consensus, we have more than this, like more problems than this. We don't want just to replicate the same state, right?
Oh, wait. Is that true? We want more than to replicate you mean in the sense that it keeps growing and changing?
Yeah. And I mean, we don't want just say if the number of replicated machines, number of replicated machines says this is the state, and we are automatically believe in this. We want kind of fine tuning and say, okay, who said that this state is correct? And
Yeah.
is this like a directly part of error correcting codes and replication, or this is like different, something different?
yeah, if you don't have trusted nodes, you need something like proof of stake. Some other way to weight the nodes or to distribute the decision process.
But we don't, but we don't completely believe in all of these nodes, because some of these nodes can be Byzantine and can be turned off, right? So in that sense, we want some kind of mechanism.
Yeah, it's probably the case that they just do that mapping of proof of stake to each single unit of stake is one validator. That's my guess as to how they treat this paper, just so that they can, consider trusted validators. But the proof of stake model would still work.
I'm thinking that if we have nodes that have error correcting codes and they will replicate without errors, can we have another layer that will be error correcting codes in our complete network that we can correct I mean,
What do you mean by a complete network?
so I read this in this coding theory that they say a transmission channel. So I'm thinking maybe we have different transmission channels, because we want the network to behave in some way, not anyway. I mean, we want to escape in these like edge behaviors that we don't want. Can we correct this and say, okay, this is something that we don't want, and this is an error, and we will correct this?
Mm-hmm.
And I mean, all the validators are giving some kind of messages, and we can say this ordering of messages we don't like. It's in economic sense.
So Tomislav, help me catch up a little bit. What's the scenario you're thinking, and then the question you're thinking through?
So I'm thinking error correcting codes for replication. This is one layer,
Mm-hmm.
and I can imagine what this means. Like it's like a RAID on hard disk, or some kind of way of replicating and correcting CRC errors, checking or something like that.
Yeah.
And when we look the whole network, can we say if someone getting all the money from the network, this is not correct behavior? I mean, can we define this these desired behaviors in that sense? Not only if you cheat on this way, we'll have some kind of defending mechanism for each attack. Maybe we can say, okay, if something like this happening, we will automatically correct this, and we don't allow this kind of stuff. Maybe in different namespaces, different way of how this works. Because for more concrete example, if you're buying parking tickets,
Mm-hmm.
totally, it's if in this namespace, if you are spending I don't know $1,000,
Uh-huh.
it's an error, because this is namespace for parking tickets, and you don't want to care about security because everything is cheap, but some kind of big amount of money to transfer, it's an error.
Oh, that's interesting. So, I mean, I've always thought of defining well, that seems like a state transition function question is sort of what I'm getting at, right? Like I've always thought of what defines a transaction as valid or invalid is your state transition function. So like, in our chain, it's like, did you reduce a COM that the channels weren't the same? Like that's invalid. Or like, did you spend more Bitcoins than you have? That would be invalid. But so are you saying like, can we somehow encode our state transition function in it, like with error correcting codes or something? Or
yeah. Like can we express our what we think is valid in more concrete way, not just by defending some block? And I mean, what will happen if we didn't anticipate all the things, and the network just goes crazy? And
oh, you're saying this almost as a like after the fact, like we wrote the state transition function one way that we thought was correct, but it turns out we didn't actually know how to express or didn't correctly express what we meant. Like, can we somehow use this as a
error correcting
answer to the DAO hack kind of question? Or?
Yeah.
Interesting. Yeah.
because I seen this problem that we have like a very good technology which is super dangerous. You know, you can lose everything because you forget your password. It's crazy. You know?
Yeah.
That's sort of what I'm working on with the Liquid Democracy, is setting up the registration in the community as a sort of island of trust, where we can agree to change behavior of things within that domain and within that area.
So I thought I remembered the reason this error correcting code stuff came to our attention was because Greg was saying something about including a notion of time into a blockchain based on error correcting codes. Have you guys talked about that at all, or do you have any idea how that might work?
No, this sounds interesting.
I thought it sounded interesting too, but I didn't know anything. Oh, well, Jim, you were on that call though when he was first explaining it to Steve, right?
Yeah. Yeah, and I was sort of intrigued by it as well, and the idea of reducing, of entropy, introducing time, sort of mirrors the the elimination of the errors, as well as creating a thread of time in the evolving evolution of the message.
Is this real time?
No.
When you care about like the delta between, or it's just the purpose of ordering, of like a relative time.
Yeah, what I understood was it was just time ordering, and that's really what we have anyway. Is each node sees things in its own order, and then when we develop a common notion of time, is when the nodes agree, or a more global notion of time is agreeing on ordering.
So you can do this by collecting some amount of all the messages from other validators.
I didn't get really what's unique about error correcting codes in this respect, because it's sort of what we do anyway is get a global notion of time when we publish blocks. We're creating orderings.
I'm wondering what is the purpose in this partial synchrony. What is how they're using time in different to what Greg was saying and with.
So I'm not really sure about that. But I remember reading somewhere about some kind of analogy between these error correcting codes and space-time. But I'm not sure I fully grasped that analogy. I don't know if anybody else was maybe a little more familiar with that.
No, do you have that resource still?
I'll look it up. I'll look for it. I want to say Jim might have sent it out at one point in time, but I'll look for it.
There is something algebraic coding theory.
That second one on the screen right now looks.
Yeah, that's like a nice little article about it. I'm sure there's a technical paper somewhere, but that's just like an expository article. Oh yeah, that ResearchGate one is probably not a bad resource.
Right next to the mouse pointer right now.
Yeah, either that one or that PDF. I don't know what that is.
Oh.
Looks good though. It's a .edu. It's probably a research paper. Only cited by 2 people since 2015 though. I don't know.
Two amazing ideas: holographic principle, quantum error correction. I've heard of the holographic principle, but I forget what it is.
That's right. They were talking about some like anti-de Sitter space or something. Oh yeah, that's it right there.
Yeah, definitely. Greg was talking about that when I had overheard him talking about this.
Yeah.
Too. You know what that is, Isaac?
No, not specifically. I mean, I think it just has some particular notion of distance in it, like a particular metric. You know, so there's like, what is it called? Like Schwarzschild space or something like that.
Yeah.
Or the Schwarzschild metric. So I think it's like another metric like that captures some particular properties that I'm not familiar with. And there's something about like we may live in a de Sitter space, but people always use these models in anti-de Sitter space because they're compact or something along those lines. They have a boundary. At least I'm kind of just rambling, but these are like the things that I remember from this kind of like ecosystem of ideas.
Yeah, I'm the ramble is welcome in my opinion.
Yeah. Oh, okay, cool. Yeah, so I can tell you like the very, very small amount of what I know about the holographic principle. I watched, I'm blanking on his name right now. I'll probably remember it at some point in time. But from what I remember of the holographic principle is there's something about how we can think of things happening in our space as kind of like being projected to some boundary, and then somehow there's like corresponding events on the boundary, and somehow that makes it easier to like deal with the dynamics that we're dealing with. But that's about all I know. What was his name though?
Did you mean this guy from Stanford? Leonard Susskind.
Yeah, Susskind. That's it.
Oh,
Yeah.
Leonard Susskind is great.
Yeah. There's
guy.
a really nice video on YouTube that's like an hour long of him just talking about holographic principle and that sort of thing.
Yeah.
Yeah, he's awesome.
Yeah.
The basic idea, if I can express it, is that when we consider a sphere of space-time, okay, we can consider everything inside that sphere to be on the surface. That's of that sphere, which is an interpretation of the holographic principle.
Yeah.
And also, what we're doing is, time is relative inside the sphere. So you have all these different relative orderings inside the sphere.
Mm-hmm.
But the creating the space gives you a notion of global time or consensus within that sphere.
Mm-hmm.
And when you say everything in these spheres on the boundary, you mean all the information and
Yeah.
what is inside the sphere?
Nothing.
The atom.
Nothing.
So,
The idea, essentially, what we experience in this world is electron interaction, and they're two-dimensional. They don't have any third dimension.
Yeah.
And all of these two dimensions, and we talk about spinning, but the potentials of the electron reverse to those of a positron,
Mm-hmm.
and then they reverse back to an electron in a half-spin cycle. They never really turn around. You never break into that third dimension in spinning. So, some people say a 3D is illusion, but and if we think about space-time and we think about, well, at light speed, the distance between things is zero. Okay, because as you approach light speed, distance and time goes to zero. Everything is local.
Mm-hmm.
So when we think about configuration space, well, we have independence, in essence. Okay, each orthogonal fold, each quantum action is an orthogonal fold, which is, in principle, independent of every other orthogonal fold. It defines a new dimension. But things will line up. Any graph can be represented in 3 dimensions. And so if it can line up with our natural dimensions logically, if it's logically possible, and that depends on the complexity of the quantum system. How many variables does the system have? If it has more than 3 variables, they can't all line up with 3-dimensional space, okay? Because they're independent, okay? I don't know if that helps.
Can you explain when you say for electron there is only 2 dimensions? So when you have some kind of charge and electron just go away from is pushed away from this charge. But you're saying this is not in 2 dimensions for electron.
No, I mean, what we have is that in configuration space, 2 electrons would occupy the same state. But that would be a logical contradiction. And so space is exhibited between them so that initially, well, you could say initially they had a velocity toward one another, and we're at the same energy. And in order to prevent that, there's an exchange where they're now moving apart. They either switch places or they exchange some momentum by some mechanism that is sort of like, it seems like the vacuum is a semi-solid that transfers the momentum between them at a distance. It's positronium. It's virtual electrons and positrons, or positronium atoms, so to speak, that enable the transfer of momentum. But what this really is it's saying, I'm not the same as you. I'm a different electron. Okay, and logically, that difference propagates as we express the quantum logical system. So it looks like they're repelling each other, but it's a quantum logical distance in terms of really. I mean, we can consider it number of events or whatever that separate them in time.
And then these two electrons, for us, they are visible in 3 dimension, right? We can collide two electrons. How this I'm not sure that I can imagine this in how this information is on boundary. I mean, because we see electron in 3 dimensions. So how you said that?
Yeah, what's the difference between the spin dimensions and the, I guess, like, spatial dimensions?
Well, the space dimensions are, like I said, they line up with our ordinary 3 dimensions. Okay, when we consider a photon has a certain wavelength, and that instantiates a space-time interval relatively. Okay, now we consider the folds to be either lateral or transverse. In fact, both. We associate the lateral with the electric and the transverse with the magnetic. When these folds enter an atom,
You're saying folds.
What?
You're saying folds. I'm not sure.
Yeah, well, I wasn't sure what word that was either.
Yeah, maybe just waves. It would suffice.
Oh, when it folds.
Yeah, I thought you meant it like a verb. Like
in the half-spin cycle, the lateral and the transverse fold orthogonally, and then the lateral and transverse fold orthogonally again.
Oh, it's a change in orientation.
It's a half-spin. The half-spin cycle involves the square root of -1 4 times. Okay. So that you've really got 4 dimensions, but it always lines up at the end, or not always, pointing the same direction in space anyway. When it hits an atom, that's another story. Now, it's in a complex system with more variables, more dimensions, and in one place, it exhibits a delay in time, local time, for the local object. Okay, when it's free in space, it exhibits extent across space. But when it doesn't line up with our dimensions inside an atom, they say that it's all curled up inside the atom. But if an atom receives a 10-meter wave, when it's inside the atom, it's still 10 meters long. It's just in another direction. That's not of this world. It's a local dimension. And that exhibits delay, local time. Outside it exhibits space, or space-time intervals that separate things. I'm not sure that we're getting off the topic here.
Yeah, this is interesting.
Yeah.
I'm not sure that I can process everything.
Yeah. Well, yeah, it would be very interesting to see where you can draw inspiration from, I guess, quantum mechanics or any of these like spatial theories, and how you could bring them into eventual consistency and consensus algorithms.
Yeah, if the standard quantum physics model isn't going to work. It isn't going to get you too far if you believe in that the universe is fundamentally random. But if you use equivalent interpretations of Bohm, Kramer, and Carver-Mead's quantum electrodynamics, it becomes sensible all of a sudden.
I just dropped a link to a PDF that looks like it's from some university class about error correcting codes. It's not about consensus or anything, but I thought it might be a nice primer for wrapping our heads around this. One of the examples is Hamming codes.
Yeah, cool.
Yeah, I've been looking for something on error correcting codes. The standard text for this subject seems to be fairly pricey and not available freely on the internet.
What's it called?
Oh, error correcting codes. Let me see if I can pull it up on my Amazon search.
Okay.
Error correcting codes, a mathematical introduction.
Okay.
By Bayless, and it's a CRC book. I mean, it's a standard. There may be better texts, but I'll take a look at this one that Joshua has found.
Yeah, I just skimmed the first couple of slides and it looked a little, in fact, maybe I'll just throw it up here just for a second to give a sense. Here was one slide that I thought was useful just when I was skimming it. At first I couldn't tell what the heck the difference was between these two like examples they give here, the block codes and the convolutional codes.
Yeah.
Then at the end I decided that the difference was with the block encoder, they're tacking on all the extra information by just appending it, whereas like here they're kind of interspersing the extra information throughout the string.
Yeah.
And somewhere in here they were talking about nature's error correcting codes, where RNA sequences encode like what represent amino acids, or I don't know like for what biological purpose, but basically they were saying like RNA has 4 possible symbols, and there's 20 different proteins we might care to represent or like spell with this RNA language, I guess, basically. And then where did it go? Somewhere I thought he was saying that they used 3 a series of 3 RNA symbols to encode all 20 of these, and so then it was like, well, okay, 3 RNA symbols I guess that gives you a space of like 4 to the 3rd, which is bigger than 20. So just like information redundancy. That's about as much as I learned so far.
Yeah, that last bullet point has it.
Oh, this one. Oh, yeah. Oh, that's why I couldn't spot it. I wasn't looking for the word 3. Yeah. So.
Yeah, I wonder how they do error correction though.
Yeah,
Or
that's
if
a
RNA does.
good question. Sometimes one or more of the RNA symbols is changed. Hopefully the resultant triplet still decodes. Oh, because, yeah. So there's like more than one correct way to spell each one, I think, or something. Because like, okay, yeah, so like all 4 of, so anything that starts with AC, I guess, is a valid spelling for one of these amino acids. That's kind of a weird way to do it though, like, because that just means like this 4th symbol is basically not used at all. But anyway, I just thought I'd share that resource.
Yeah. It's interesting because like if you look at that aspartate and glutamate, like bottom right and then go to the left one, it's like there's a distinction. So you can do GAs, and then depending on that last one, it's going to be the aspartate or the glutamate.
Yeah.
Yeah, I could see this table as like a namespace hierarchy. So maybe that's kind of how it evolved. It's just slapping on another code for changing amino acids, and maybe those 2 amino acids at the bottom right have some kind of like close similarity.
Yeah, and this is a highly simplified view in that most of the DNA doesn't specify proteins at all. This is just showing part of the process. The thing is, there's random mutations all the time due to cosmic rays or whatever.
Yeah, noise in the line, right?
And generally they're corrected. If you have a healthy system.
Yeah, I think they're usually they're corrected because they die off. They're not viable. And the ones that are weakly viable are the dangerous ones, or the carcinogens.
Interesting.
Yeah, but error correction happens on many levels in nature.
Yeah.
Yeah, I mean, I guess for DNA, it's a little easier if they don't have a state transition function, then they can basically just look for exact replicas or not.
So wait, say that again, Jay. What did you mean there?
Basically just, we were talking about for the error codes, like it'd be pretty easy to reach some kind of consistency if, you're just trying to reach consensus on one error code. But as soon as you have a state transition function where, people can spend money or two different things. In relation to DNA, I guess they don't necessarily have that unless you consider like epigenetics or something like that. But that makes it a lot easier because then you can just do like survival of the fittest, basically, or odd one out.
Yeah. Cool. All right. Well, I'm curious if Tomislav has any Rolang stuff to show us, or anybody, I guess, has any Rolang stuff.
I really have something for you, Josh.
Yeah.
Yeah. I was inspired by this talk from Philip Wadler. So I have like a really good example for deep and shallow embedding. And
oh yeah.
And final and initial.
After last week you removed the shallow one, right?
Yeah, but now I want to show this like a very simple example, not related to rolling at all.
Oh, cool. Oh, great.
So yeah.
That's awesome. Yeah, let's do it.
Oh, should I do it first?
Yeah, I'm ready.
I was wondering, before we go to Rolang World, I was wondering if anybody looked into this paper that you posted, Thomas, on a proof secure block of proof of stake blockchain protocol.
Yeah, I'm interested to learn more, but I don't know a lot. No.
Oh, that was
maybe
that
next
video was the one you posted. I think one above.
Yeah. So I was looking at this consensus, but it's semi-synchronous, which is I think partially synchronous. Is the same, I think, and they have time slots for they have a leader election, and they have two versions. This new version is a private leader election, and this first version is a public leader election. And they have time slots when each leader who is responsible for this block is publishing the book. And I was immediately think about Casanova, and they have something similar, right? They have some scheduling, but they are leaderless. So wondering.
Definitely Hashgraph had the scheduling, right?
Yeah, I don't know if Casanova had scheduling at all.
Yeah, I don't think
Casanova. It seemed like everybody just builds their DAG all at once, kind of, in Casanova.
But they have some way to say that publishing block will be in regular intervals.
Yeah, so they had an upper bound for the length of time that it takes to deliver a message.
They have also the same.
Okay, yeah. Yeah,
but
yeah, maybe that's the partial or semi-synchronous part is just like some upper bound on delivery time of all messages.
Yeah, Casanova also had like a subgroup assignment or something like that, where there were like smaller teams that were all creating blocks in parallel. Okay. I mean, so maybe there's some kind of leader selection for that. I'm not sure. But yeah, for Ouroboros, they use the follow the Satoshi algorithm. If you've heard of that one for leader selection.
No.
It's basically just you lay out everybody's stake on like a number line. So like if I have 10 stake and Joshi has 100, then I might be all the numbers 0 through 9, and then Joshi could be up to 99 or 99 plus 10.
Oh.
And then you just randomly choose a number and see where it lies and who owns it, and they become the leader. And the nice thing is you can do that for like a few. So you can select, 10 leaders for the next consecutive round, so you don't have to do it each round, which is, I guess, improves some efficiency. But it's still definitely an older idea than Casanova. I don't think it's going to be quite as efficient as Casanova.
And you are describing the first version. And the second version, this porous, I think it's called Alvarez porous. In this version, it's a private leader election. So yeah, and I was just wondering if you have some kind of scheduling, is this implies that you have some kind of leader election? Because you're saying that there will definitely be some number of blocks in this period of time. So who will make the blocks?
I remember reading Vitalik's write-up of Vlad's CBC Casper, and he said something like all of just assign all the validators an integer, and then number your time slots also, and then when the time slot mod n is your validator number, that's your turn to propose a block. But that's totally deterministic then, right? Like I know in advance when all my turns are going to be.
Yeah.
Yeah, but I mean, that's not really a problem as long as everyone else knows too.
Well, my thought was if everybody knows when I'm supposed to propose a block, then everybody knows exactly when is the right time to try to DDoS me.
Yeah, exactly.
Hmm.
And they were talking about if you know IP address, then this is possible. So maybe you don't, maybe IP address should be hidden. But how can you?
Yeah.
Yeah, that's a good point.
VPN. No, I'm kidding.
Yeah, and that's a really bad combination with, I guess, Ethereum's new, or what they proposed for Casper, which is like some really high staking number and like preferences given to validators that have been in the pool for a very long time. So like basically the more well-known you become, the more susceptible you are to a DOS attack.
Yeah.
Shall we go to the rollback now?
Yeah, sure.
Yeah, definitely.
Yeah.
I should stop recording and start again.
Restart the recording?
Yeah.